Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right.
And we made it.
And we made it.
We made it.
Hello,
we did it.
everybody.
99 episodes.
Mm-hmm.
Today is 99. It's like this episode doesn't even matter. Can we just stop? We're just going to cancel. And we'll start over in 20 minutes. We'll just like ready, break, and then that's 100. Because 100 is 100 means something, but 99 is like, well, who cares? You didn't even make 100.
Yeah.
Still double digits.
Still double digits.
It's like, does it even matter? Does this episode even matter? Does anybody have a question about electrochemistry? There are questions about electrochemistry. But I'm very excited for the next episode because it's going to be 100.
Yes.
And we just have to get through this one.
Yeah.
And pretend that we care. That's so depressing.
No. We care. We care about every episode. Every episode is a special episode.
You know what? And I've not been aware of the numbering, like where we're at for a long time, and then suddenly you become aware because we do the timestamps, we do the whole thing every week, and it's like, oh, I guess we're at 80 something. Oh, that's kind of cool. Now it's 99. I'm like, oh my gosh, we're so close. I can taste it. I can taste the triple digits.
Yes, the anticipation.
I know, it's amazing. And you know who's ready for episode 99? Ahmed Hagazi. Because this person, I believe, has asked the first question.
Yes,
chronologically. So this questions were 30, 40 or so minutes ago. So thank you, Ahmed, for questions. We'll get right to it then. So we can get this over with and get to number 100. And Ahmed says, if LSV shows faradaic current below 4 volts, does this imply that electrolyte is unsuitable for high voltage cathodes operating at greater than 4.3 volts? Could such electrolyte still function with limited cycle life? There's a bit of a continuation here, or reduced capacity. Is a rest. Okay, so I think, and then the next part is a little bit of a separate question. So I'll try to answer this first part. I think that it's possible. The answer is yes. Okay, so I want to be clear. It's not a guaranteed no-go. For instance, if you're studying a cathode material, and you're noticing some strong faradaic reactions occurring at lower potentials, it could indeed be an indication that there's an instability, unsuitability, whatever the right term is, of that material, because it's reacting with the electrolyte, right? It might be ripping the electrolyte apart. And in fact, if that is happening, yes, that would mean that there's an incompatibility, whether it's the electrolyte or the cathode, right? I mean, it could be one or the other or both or something like that. But certainly if the requirement with a lithium battery, as is often the case, to operate at voltages between 3, 4, maybe even 5 volts, depending on the situation, if those voltages are unstable with the combination of electrode and electrolyte, then it does preclude their usage. So I'm not going to say 100% yes, because maybe there's some small faradaic reaction, but maybe it's just like it's a change of oxidation state of some kind, and then it's stable. Something like that. Like that might be the case. For example, your cathode might be a transition metal oxide material of some sort, and it oxidizes above 2 volts to some state, but that's the state that it just exists in as a cathode. You might be mistaking a faradaic reaction with just the state of the cathode as it is meant to function. That might be okay, right? So you'll have to find a way to differentiate what the reaction is if it is decomposition of the electrolyte, which would be a bad, don't use that material, right? Or if it's just some state of the material, that's fine. Check on which of those is happening is my advice to you. So cautiously, the answer might be no, but it might not be as devastating, I'd say, but that's a great question, for sure, because those are things that you do need to take into account, for sure, when you are selecting materials for a battery. The next part of your question, let's see, is a rest period necessary for lithium aluminum coin cell before conducting LSV? If so, how should the appropriate duration be determined? What's that?
Aren't you usually on the fence about doing LSV of batteries?
Yeah, but so yeah. um, I am from the perspective that a lot of folks approach battery electrochemistry in the same way they do traditional electrocatalysis, which is incorrect. Which is to say, they might just load up some materials in a 3-electrode system. Uh-oh.
Nope. No, you're still good.
Are we good?
I think we're good.
Okay, check all the things I just saw.
Yeah.
Connected, disconnected. There's all the streams and things. I hope we're good. Okay.
Yeah, I think.
So just connecting your system and trying to do CV at 20 millivolts per second, that isn't appropriate. That isn't how batteries work. However, if you're doing LSV at a very slow scan rate, 1 millivolt per second or slower, certainly it is something that is done pretty frequently, like usually as the first step, as a diagnostic to check for those faradaic reactions, hence the first question, right? You're checking for, if you, for example, if you're testing a material that you think will work as a cathode or an anode, but you're not sure, because in theory, it should intercalate or deintercalate or hold lithium, but you don't know. Theory guides, experiment decides, right? You can do CV and you see no peaks. Okay, well, even scanning very, very slowly and deliberately, you see no peaks. It's just flat or whatever. Well, then experiment decides that this is actually not working for one reason or another. So it's still okay to do LSV or CV for sure. In general, it's a good idea to wait some amount of time before, when you set up an experiment, run an open circuit voltage, open circuit potential, experiment for 30 seconds, 60 seconds, and just see that you have a stable voltage. If it's drifting like crazy, something might be off, or it's just taking a while to achieve a stable surface. But if you're working with battery materials that you are relatively certain are appropriate or will function, it's not necessary usually to let it sit for an excessively long time. You can usually start your first cycles, which is usually to form the SEI and kind of get usually it's like loading up one side or the other with lithium is sometimes the first step to get your battery in a state that it can start being charged, discharged. So I would say, as a general rule, yes. And appropriate duration, again, it sort of depends on what it looks like, but if you have a relatively stable looking OCV, then less than a minute should be sufficient, probably. And then the last question in this line is that what is an acceptable range of discharge capacity variation over cycles to consider a coin cell stable? For instance, would a 1 to 5% fluctuation be acceptable, or are stricter thresholds required? So I would actually say that it should be pretty tight. I don't know that I can really give a firm number. I would from my experience testing coin cells, if you're doing like 10, let's just say like 10 or 20 charge discharge, galvanostatic charge discharge cycles, like simple, like C/5 up, C/5 down, whatever, right? Maybe there's an OCP step in between, just a very run-of-the-mill simple thing. And you're getting more than like 2 or 3% deviation. And I'm not talking about like, maybe you get like, okay, you charge up and you charge up and then you discharge. And let's just say it's like 100 milliamp hours, right? And then the second one, you get 97. And the third one, you get 93. And then the fourth one, you get 86. Well, that isn't deviation. That's deactivation. Like maybe your material's poor, which is fine. You're learning something about your material. It's okay. But if you do 10 charge discharge cycles and you get 100, 115, 92, 107, 86, that's a problem. That is definitely a problem. I'm not, it could be any of a number of things. But I would say that if the deviation is sort of random all over the place and not in a pattern that suggests the materials deactivating, or there's some some explainable problem, right, with your material, for example, and it's kind of deviating a lot. I would again, I don't 5%, I suppose, sounds reasonable. I would think it would be even tighter than that, because a coin cell that's made well, properly, and it takes practice, it takes time for sure. Even just like a quick 10 C/5 up and down, you should get almost the same number every time, like almost exactly the same number. Like it probably should be within 1%, if I'm being honest. So if you're getting a lot of variation, I would say that is probably unacceptable. And you should probably, it might just take practice in making the coin cell again. So that's a great question. These are all really great questions, Ahmed. That's my take on that set of battery questions there. So.
All right, we did get well, actually we have a Porvis question.
Yes,
next technically came in after Ahmed's, which is it okay to use silver chloride, saturated potassium chloride reference electrode in highly alkaline solutions like 1 molar potassium hydroxide? Generally speaking, it's you might be able to get away with it for a little bit, but generally speaking, you want to use an alkaline, specifically an alkaline reference electrode like mercury oxide. What tends to happen is in highly alkaline solutions where the pH is like 14, or if you have like 1 molar is pretty concentrated. If you went higher, even more concentrated, you'll tend to dissolve the glass that's around the silver chloride reference electrode. And even some of the frit materials that that silver chloride reference electrodes are made out of are either glass or some kind of ceramic. Those tend to dissolve in highly alkaline solutions. So that process can be a little slow, but it does happen. And when that happens, you almost get like a fusing, sort of say. It's like if you're dissolving the frit or the glass, all the pores that make up the frit will start to gel together, if you will. And that tends to lead to a kind of a blockage, really. So instead of having a porous membrane or a porous frit, you have kind of a solid piece that's there, and then you get problems. So while you might be able to use it initially for a little bit of time and get good results, things are stable, it will go bad over time. So it's recommended that you don't use a saturated silver chloride reference electrode.
And I think just for reference, Pine sells a single and double junction silver chloride reference electrode. And I believe in our documentation, our recommendation is greater than 0.1 molar. In other words, don't use in greater than 0.1 molar KOH. So it's a bit of, as you said, it's like the stronger the KOH, the faster that things are probably going to go haywire. As a general rule, 0.1 molar KOH and lower, probably going to be okay for relatively extended periods of time, but stronger and 1 molar certainly is considered pretty strong. You're going to start to see those problems. So just to give a number on it, that's what we recommend.
Yeah.
Okay, let's see. Nicholas is here.
Yeah, Nicholas is here. Says hi.
Let's see. Nicholas. All right. So his question is, could you guys speak a little about OCP and PZCs as potential of zero charge? Is there a direct correlation between these potentials? When the OCP is at or lower than the potential of zero charge, for instance, how could I understand the surface? Man, I hate this concept.
I know. I'm still trying to wrap
your
my
question
head
is
around
fine,
it.
Nicholas. The potential of zero charge is a weird one for me. Honestly, it's like, it's a thing. Like it's a whatever, a real
A real
quantity or whatever you want to call it.
Yeah.
But it's just as it says, it's the potential at which net charge is zero at the surface. And no, that's
Yeah.
not necessarily open circuit potential.
Yeah. It's hard. This is the way I think about it. So hopefully this
Okay, can we
maybe
stop for a
this helps.
second?
Oh yes.
Why does undo work for you?
Why does undo work?
Why?
Oh, Control Z.
You just did that. You drew lines and you did
Control Z.
every time I do that, my PowerPoint crash. You've seen this,
Oh
right?
yes, I have
My
seen
PowerPoint
this.
crashes every time I do this. I'm sorry, I'm waylaying things. I can't undo any drawing. That's when my PowerPoint cancels. Draws my
I can undo it. I can undo that too. I don't know. I'm sorry.
You have special undo powers. Anyway, I'm sorry. I noticed that you worked for you, and I'm sad that I can't. Please continue.
Yeah, I'm just gonna talk maybe generally about it because I don't know if I can answer your question exactly, because it sounds like it's a thing that's maybe even more complicated than I think about. So this is your electrode potential, sort of say, and let's say, and it's in solution, something like that. The way I like to think about this is there's what's referred to as the inner potential of the metal electrode. And this is a, I'm going to abuse the undo button a lot.
Now you're just teasing me.
Yeah. So, this is something that's referred to as the inner potential of the electrode. And this is a unique feature, if you will, of the electrode, which, and it's based on the surface and things like that. And this potential represents like how easy is it to move charge within the metal electrode? Well, it's pretty low. It's pretty easy to move charge within the electrode. But when you have an electrolyte solution, there is a potential of your solution. And it's this potential difference that tends to cause, I'll just use a dashed line here. It tends to cause this, like you end up getting like either negative charge here at the electrode surface or positive charge. I'll put pluses here just to make it kind of clear. This is what creates like the double layer, sort of say. And when you have another electrode in solution or in your system, there it also has a phi, and it also has an S, sort of say. And when you measure the voltage between these two, because this is what we can measure experimentally, what you're doing, I'm just going to call this M2, I'll call this M1, and the solution potential, let's say it's the same. What you are measuring at your voltmeter is phi M1 minus the solution potential minus the IR contribution, which is very small. It's very negligible, but you need a small amount of current with an IR drop to make this measurement, minus phi M2 minus phi S. Now, in this particular case, phi S cancels out. Actually, this is the difference between these two. So sorry, this is actually because it's the difference between these guys. We can think of this as a quantity. And then this is basically nothing because it's effectively zero. And then minus the difference between phi M2 and phi S. And in this situation, the solution potentials cancel out in this situation. But typically what ends up happening is you're not using just any old electrode. You're using a reference electrode. So your phi S is actually different. This whole quantity here that you measure is really ref, right? That's what this whole guy is. So when you're actually making a measurement, the open circuit potential, because this is all equal to the open circuit potential, is really this phi M1 minus phi S minus ref. That's really what it comes down to. Now, the potential of zero charge in this picture, which I'm not 100% sure, what I believe is that the potential of zero charge is when phi m. Oh, it should be a phi.
Use the undo. There you go.
There's use the undo. Phi m1 is equal to phi s, because it is because there is a difference between these two guys
That charge builds up.
that charge builds up on the surface. You want to get to a potential where there's zero charge. And that's the potential where these guys are equal to each other. So, there's that idea behind it, and your reference electrode is your reference electrode potential. So sometimes I think that if the OCP is equal to the opposite of your reference potential, you get a condition where, like, oh, that's the potential when you've moved the potential of your phi m to be equal to phi s. But what tends to happen in electrochemical systems is that this phi m is a function of it's a function of the redox species in solution, which is based on the Nernst equation. I have to throw in the Nernst equation in here. So determining like what this is, because this value can go up and down just based on redox species in solution. And even if you have dirt in your solution, some minuscule little thing like oxygen, there's kinetics associated with it. Like oxygen will change, or whatever's kinetically fast will change this phi m. So finding the potential of zero charge for any particular metal or system, unique to itself, will differ because of what this value is, and this value can change. So I think that kind of, I don't know if this is very helpful, but this like describes the complication associated with determining the potential of zero charge and its relationship to the open circuit potential. I still need to read a little bit more about it. This is my kind of stab at understanding the potential of zero charge. For electrochemistry with 3 electrode systems, it's a little bit easier. We have more tools to solve it, but the potential of zero charge also exists or the point of zero charge exists for things like nanoparticles in solution, and that's something where it's harder to understand or calculate things. So hopefully that was helpful. Hopefully, Nicholas, this was a little bit helpful. I'm not so sure. I may have to do some more research on
It's not
this.
a concept that I feel like I've a lot of experience with either.
Yeah.
And I think that it's one of these things for sure that's not well understood in general, I would say.
Yeah.
Right? As a concept, it makes sense. Like, oh, net zero charge. Like we can
net zero charge.
We can understand that. There's some positive going this way, there's some negative, but overall the net is zero. Just like we can conceptualize current. OCP is net current. I mean, I guess that's another, I don't know, very simple way of looking at one. OCP is where the net current is zero. Zero charge is where the net charge is zero. Those aren't necessarily the same things. But I mean, we can conceptualize some's going this way, some's going that way. But in summary, it's zero. But the charge thing is weird. I think for me, it's weird because I don't think that explanation is really nice from like the different potentials that are present from the solution in each electrode, basically.
Yeah.
But what throws me for a loop is that charge is time based.
Yeah.
Like, right? Like just in general, charge is the integrated current over time.
Yeah. Yeah. Well, the current is the charge over time. So you can have charge that's just like static. It's just like there. But unless it's moving, you're not going to measure it, right? Because we can really just measure a current.
Right.
It's only when it moves do we measure it. So but,
I just think about a Cottrell equation, like the current is whatever, and the amount of charge is changing over time as a thing has, as a double layers building up or whatever, right?
Yeah,
setting up
diffusion or something.
And so it's like zero charge. Well, like at time is half a second, there happened to be zero charge net going both directions, but then a half a second later, it wasn't zero. So that's what it messes me up. It's like, that's why, like, well, what potential? Well, what time at what potential?
Yeah.
For me, that's where I get a bit confused trying to conceptualize it, I guess.
Yeah.
But anyway.
Yeah. It's
so hopefully that kind of, I don't know, gives you a little bit of theory about it, Nicholas.
Yeah.
So, until then, we have any more information, we will move on here. So Jiri Shankar has a question. Is it possible to calculate the number of active sites from CV or LSV data. I'm trying to calculate the turnover frequency to prove the intrinsic activity of my catalyst. Active sites? I don't
Yeah.
know. You can definitely calculate the ECSA.
Yeah.
So, in short, I'll draw for you just this concept that is fairly well known, and apologies if you sort of already know this and this is rudimentary. But for those that aren't, the electrochemically active surface area for platinum, for instance, involves looking at the cyclic voltammogram of platinum in something like sulfuric acid. I don't have any space. That's why that oxygen reduction looks terrible. What we do is we basically get the area under this part and or this part. Okay. Because this right here is the platinum hydrogen. This is the desorption up here. And down here, I have the platinum hydrogen adsorption. And what we know from, and I actually have the original reference. I dug it up once upon a time, where this comes from. But we know that platinum hydrogen adsorption desorption process is associated with an average. It depends on the crystal facets, but it's an average of 210 microcoulombs per centimeter squared. And so what we can do is very simply, this is voltage here. So what we do is we instead go to the current versus time of the adsorption, desorption. Speaking of zero charge or whatever, we get this. So we integrate I dt, basically. That gives us the charge, right? And that's a certain number of coulombs. So we have X coulombs. And so we take, sorry, this is like convoluted here. And someone asked, do we send these slides publicly? You don't want this slide. This is a mess. That's why this is like deconvolute this slide from what I'm saying right now. Hopefully you're following along with me as I'm drawing this. But if you're looking at this slide later, you'd be like, what was happening? So that's mainly why we don't share these slides. I mean, I could save this and send it to you if you want, but I'm not sure this is useful, to be perfectly honest. So we would take X coulombs that I measured from this integration divided by 210 microcoulombs per centimeter squared, right? And that gives us whatever Y centimeter squared. Now, that is surface area. I suppose it's possible. Like, is there some conversion between surface area and active sites? Like, is there, and this is an open question. I don't know the answer. You might be able to say, like, well, if I have this much square centimeters and the average active site or single crystal or molecule, or I don't know, whatever, has this much area, maybe you can do a quick factor and you might be able to come up with some answer. But the precise number of active sites, I don't know of a method apart from that specific electrochemically active surface area, which again is sort of tangentially related. But like, I mean, the other thing is, I guess, like, frankly, wouldn't the number be massive? Like, this is like on the molecule level, right? Like, how many sites? Like 10 to the 20, 10 to the 30? Like, wouldn't it be, I mean, I expect that number would be large, right? Like, or am I not thinking about it right?
Well, I guess, it depends. Like, if you have a, I think you're generally right, but like, so the number of, like, surface coverage of molecules is typically on like the order of 10 to the 13, 10 to the 14, like, molecules per square centimeter. So if you have a big molecule, it's big. There'll be fewer molecules per square centimeter, but that's like the rough order of magnitude, sort of say.
Yeah.
But if you're talking about a catalyst,
well, he has a follow-up question too.
There's a follow-up question.
Says, I know how to calculate the electrochemically active surface area from CDL. I need the number of active sites to calculate turnover frequency. Or can you show another method to calculate the turnover frequency with the workstation?
Well, so the turnover frequency,
I mean, I think it's a kinetic thing.
It's like a catalysis thing because he has a catalyst, and then so you have a certain amount of catalyst,
Yeah.
and then you have a substrate that you're adding to the catalyst. And let's say it's a 1-to-1 molar ratio. So for every mole of the catalyst, it can generate 1 mole of the product.
Yeah.
So if you added, say, like 1,000 mole, if you have 1 mole of the catalyst and then 1,000 moles of your substrate, and you were able to get like 600 moles of your product, then you'd have like a 600 or whatever turnover frequency, something like that. Because it means that catalyst did 600 reactions before it died, right? That kind of thing. Usually, yeah, I'm thinking about like you do like a chrono-potentiometry or chronoamperometry experiment. You hold the potential, you look at the charge over time. You're looking at like the faradaic efficiency, sort of say, and you can almost go at it from either a weight perspective, how much weight of the catalyst. It depends on if you have a heterogeneous or a homogeneous catalyst to a certain degree. I'm guessing it's a heterogeneous catalyst, but I don't know for sure, because depending on those two things, it's like there's surface coverage and the active sites, but then it's just like, well, how much, like when you do catalysis, that's how you determine the number, like the turnover frequency, like how long did you run it before the catalyst died or the activity decreased. So yeah, unless you're doing something like scanning electrochemical microscopy for like the real atomic imaging of active sites.
The equation has Avogadro's number of the numerator and the number of sites in the denominator. I guess that's one equation, right? I think you're probably looking at, that's why you're thinking about number of sites.
Okay.
I think that, I'm just looking briefly at some other possibilities, and I'm trying to think about it in terms of an electrochemistry perspective, obviously.
That's the turnover frequency calculation?
I guess it's one version of it. I think there's probably
Okay.
there's a number of ways. Like it's as you described. It's like how many times does this thing do the
Yeah.
reaction before it dies, or
Yeah.
or per
How often is it churning over the catalysts? Or
per catalyst.
Yeah,
So
per
whether you're
catalyst.
saying that's active sites or concentration or
Yeah.
moles or
Mhm.
grams or dollar bills underneath your mattress, whatever, per thing of your catalyst, how
Mhm.
much is it making?
Yeah.
Right.
Yeah.
So active sites is just one possibility. So I think that one
Mhm.
thing to say is that the formula you're using for turnover frequency involving active sites might not be the only one to use. For example, even just a quick like search, you could have things like the reaction rate divided by the concentration, and the reaction rate, if it's like a first order rate constant, you'll have like concentration per time. So concentration cancels, you have 1 over time. It's like a frequency, right?
Yeah. It's a frequency.
So if it's concentration based, fine. And then if it's a rate constant, that's a chemical thing, not an electrochemical thing. If it's an electrochemical thing, I'm just thinking out loud, because again, it's like you're asking in terms of like the potentiostat, the workstation. What do I do? Well, if it's calculating a heterogeneous rate constant, that's usually like centimeters per second or something like that, I guess.
Yeah. Centimeters per second would be like the rate
So
constant for heterogeneous.
right. So like from an electrochemistry perspective, thinking about this concept, I suppose you could, in theory, get the heterogeneous rate constant through one of the several means that there are. And then I don't know what you would divide it by, because what centimeters, what length unit would you divide by to normalize to get your turnover? You know what I mean? Because
Yeah.
it's not concentration.
Yeah.
I have open questions about this, and I understand what you're saying. You're saying, how do I do this with my workstation, with my potentiostat?
Yeah.
And that to me is the not clear part of this, because I do think, for the most part, this turnover frequency is a phenomenon that's more chemical than electrochemical. I'm not saying it isn't possible, but that's why my mind is going to heterogeneous rate constant, because it is fundamentally a kinetics divided by catalyst material, something, concentration, active site, something like that. But the numerator, for example, involves the speed or the kinetics of the reaction. And so from an electrochemistry perspective, the heterogeneous rate constant, which is like tied to the the exchange current density or exchange current, for instance. There might be something that you can do there, and I'm not 100% sure if there's a expression for the turnover frequency within that context, because most of it to me appears to be largely chemical and not electrochemical, so to speak, I guess. But I certainly could be not aware of the appropriate way to do this.
The other thing I'm thinking about this for like the homogeneous case, but literally the difference is like one way people get turnover frequency is they get a CV without the substrate. So catalyst without substrate. So the non-catalysis thing, you get like a duck shaped thing. Then you add an excess of the substrate to your system. You do the same CV under now it's under catalysis. You see a huge increase in current, right? This massive increase in current at the same, and you look at the ratio of the current with catalysis versus the current without catalysis. And that's a way of, because that literally in a way is how many turnovers, how many cycles are you getting? Because when you're at those potentials, normally you have diffusion control. But if your molecule like, okay, it oxidized my catalyst, so now it's active, it's diffusing away. Oh no, it reacts exactly with an excess of the substrate. It's now back to the normal state, and I'm really close to the electrode surface. It's just going to diffuse back and then get another, do another, redox reaction. But then it's next to another substrate. It's going to keep doing this. It's going to cycle. So you end up getting this huge current under the case of catalysis. And that is a way, an indicator, if you will, of how you can get some level of turnover frequency, because it's literally turning over many, many, many times at this same potential. And catalysts that work better than others, have a much higher current than, during catalysis versus not catalysis. But in the heterogeneous case, because you're talking about active sites, I don't know if that works as well. You may need, because you still run into mass transport issues. It may be a rotator case. You may have to use a rotator with and without the catalyst to do that kind of same reaction, because you run into a mass transport issue. I think maybe that's one way to go about it to get the turnover frequency.
Yeah.
Yeah, I don't know.
To be honest, it will require a little more research probably on our part. And you might have to do the same. I mean, to be honest, I think that the best general advice I guess I would give is that the method you're currently stuck on with Avogadro's number and number of active sites might not be the best expression to be fixated on. It might be that you need to find an alternative equation that's more able to be interrogated with a potentiostat. And yeah, sorry that we can't maybe give more specific, we're not maybe aware perfectly well, but there's probably a way to calculate it from an electrochemical perspective that's a little more appropriate using a potentiostat. So but good luck with that for you. All right. See, the next question here is from Stupid Man. Well, that's not nice.
That's not nice.
You should have higher self-value than that. But okay. So he says, is it possible to determine the surface area of an electrode with amperometry? Is this reliable? What do people generally use to reliably determine the surface area of a carbon fiber microelectrodes? So yes, it's possible. No, I don't think it's necessarily the best option. You can use the Cottrell equation. You probably have it popped up easily. I know we have an overlay, but you have it's in here somewhere.
Well, I think it's somewhere.
Is it in here? It must be in here.
Tafel.
Cottrell equation.
I think Cottrell's back. I just figured I'd jump to this.
Yeah. No,
there we go. This is Cottrell.
Yeah. So here's the Cottrell equation. So what you can do, for instance, is amperometry. So chronoamperometry, which is you apply a certain potential and you measure the current over time. What you'll generally get is a decay a decay of the current, right, by the square root of time, hence the Cottrell equation. And then what you can effectively do is make a plot, for instance, of current versus 1 over the square root of time. And if you just look at this expression here, I'll share.
Yeah, we can just share screen because I was like, oh, we can't actually share it.
Yeah, that's okay. I'll do this.
Yeah.
Here. I'm going to butcher it. I is equal to, hang on. I is equal to, it's, what is it? NF,
yeah, NF D to the 1/2
and
times C divided by
the square root of pi t, right?
Yes.
Oh, so
you got it.
I got it.
Oh, you got it.
Look at that.
Yeah.
It's like I'm an electrochemist or something.
Yeah.
So if we plot, for example, I versus t to the minus 1/2, basically, right?
Yeah.
What are we left with, right? Well, we're left with, oh, I'm not going to undo. It's going to break. I can't. I'm going to just write over it. There we go. We're left with all the rest of this. Here. So one of the things with the Cottrell equation is that it is often used to get the diffusion coefficient. But if you just know what it is, or you can assume a value for D, you can use this to say that the slope of this plot right here, because so the amperometry that you get, current versus time, is something like whatever, it's a decay, right? But when you plot current versus t to the minus 1/2, would the slope be positive or negative? Is it positive usually? Does it matter?
Oh, what? Sorry.
Is the slope positive or negative when you do t to the minus? I think it's probably positive because all these values are positive. Let's just say it's positive.
Yeah, let's just say it's positive.
Okay,
that's fine.
So anyway, you can get a slope, right, of this.
Yeah.
Okay, great. And your slope is basically equivalent to NF A C D to the 1/2, and I guess there's a square root of pi in the denominator. Who cares? Okay. The point is, if you know all of these constants here, if you know N, you know F is Faraday's constant, you know the concentration, and you can make an assumption of the diffusion coefficient, like something about your electrolyte, for example, then you can calculate A. This is a way to do it. Now, your other question is a good one. Is this reliable? It's a good question. I mean, you can make an argument that you're making an assumption, right? You're making an assumption. Well, you probably know the concentration pretty well. Hopefully, you know the number of electrons transferred if it's a predictable faradaic process or something. Is the diffusion coefficient accurate? Okay, sure. So there's some open question how reliable it is. I suppose it's relatively reasonable thing to do to calculate it. But if you're asking how do people usually determine the surface area of carbon fiber microelectrodes, it's probably through non-electrochemical techniques. Things like Brunauer, Emmett-Teller, BET analysis is the way that people usually get specific surface area. So this is a technique that uses nitrogen isotherms on a material. It's a physical technique. It's not electrochemistry. It's a physical characterization technique, and it gets you to like square meters per gram, basically, of a material. And that's actually a way people often get the surface area of materials, for example, the mass specific surface area of a material. And then you are making an assumption, for example, when you put X milligrams onto a catalyst, that ratio is the same. So you put like 2 milligrams of a film of your carbon fiber onto an electrode, and you have 10 meters squared per gram. So you can figure out how many square meters of surface area there is, for example, like things like that. People that's how a lot of times that's done. But you could, for example, do that if you have access to that equipment, and then do your amperometry experiment with values that are reasonable and see if it matches up. Hopefully it's relatively close. You might find that, for example, if your catalyst layer is really thick, you have mass that's stuck, for example. So sometimes your amperometry might be indicating a lower area, and that's because there's, half of the milligrams are not accessible, for example, because they're like, it's a film and it's certain thick, and all the stuff underneath can't be accessed by the solution. So it's like that surface area is inaccessible. So some of that stuff might play a role, which is tricky to predict, especially when you're making thin films. So I don't know if you have anything to say about that.
No, Stuman had a comment. He just said, hi, thanks. What is the analyte to use for the Cottrell equation, any redox probe? So you can use any analyte. Ideally we recommend simple redox species. Ruthenium hexaamine, if you're in aqueous systems, works very well. It's extremely well behaved, fast electron transfer kinetics. If you're doing non-aqueous electrochemistry, ferrocene works really well. So those are both good redox probes. You can even use ferrocyanide for aqueous if you want something a little less expensive than ruthenium. But yeah, any redox probe where you're able to, if you know the diffusion coefficient already, that can help you determine the area. So yeah, hopefully that's helpful.
Okay, we've got a lot of
We
questions.
have a lot of questions.
We're getting through them as quickly as we can. But all right, let's see.
Apoorva has a question.
Okay, so is it possible to know the solution resistance of a platinum ring in RRDE? And if so, what is the technique that can be used in aftermath? So the solution resistance can be done in aftermath. I would say, in theory, the solution resistance should be independent of ring or disk. It's a solution property. Does that mean that if you run it on the disk or the ring, it will be the same? Probably not, because this is electrochemistry. Yeah. But in theory, it should not be impacted. Now let me back up a bit. The solution resistance, specifically, as you've said, is a property of the solution, right? But what you measure as uncompensated resistance or RU, IR drop, whatever, that can actually, of course, be different because the electrical pathway to the ring is a little different than the disk, and minor differences between that electrical pathway are all captured in that uncompensated resistance. So, for example, the uncompensated resistance that you measure will be impacted by the solution resistance, as well as the brush in your rotator, the cell cable, the connection between the brush and the cell cable alligator clip or whatever, the electrical path between the shaft and the ring, and all of those things impact it. And yeah, of course, it's ever so slightly different between the disc and the ring. So the value you measure will be a little different. But in aftermath, it's actually quite, don't I have it open? I do have it open. Why aren't you showing up for me? There you are. Okay. It's actually quite simple. So there's an impedance method called impedance RU, EIS RU. And so this is the method that you would do. Now if you're calculating it for the ring, what you're going to do is you're going to, the potentiostat has, I assume you have a bipotentiostat if you're doing a ring, right? So there's a red and an orange lead. That's the working electrode 1. There's a blue and a purple lead. That's the second working electrode. Normally, the second working electrode, the blue and the purple, is connected to the blue brush, the bottom brush on the MSR rotator, or if it's a wave vortex, it's like I forget which side it's on. Anyway, the blue brush. And the red and orange cables from your potentiostat connect to the red brush, which is the disk. So if you want to just calculate the RU of the ring, ignore the blue cable, leave it loose, plug the red cell cable from your potentiostat into the blue brush. Now you are just studying the ring. The other two electrodes remain the same, counter and reference. Those, whatever those are in your solution, your cell, I assume, leave those the same. So you're going to connect the working electrode to just the ring and leave the second electrode. So you're going to do impedance basically on the ring by itself. And so this experiment right here, you can just use the default parameters. It's probably going to be fine. And then when you run, I don't have a potentiostat connected right now, but you would click perform and it will interrogate the uncompensated resistance for you automatically. And then you'll have the solution resistance slash RU for your ring.
Of course, if Porva, also let us know. That's if you have like a wave driver 200. If you have something different than that, EIS RU might not be available. So let us know. Additionally, double check what version of Aftermath that you're using, because we do update Aftermath, and on our website you should download and use the latest version of our software. So yeah,
I'll put a link to that in a moment here.
Yeah.
So here's the downloads page on our website. where you can download the latest. It's called Aftermath Blue. So if the version you're using, for instance, is green in color,
Mhm.
We just called that one sort of Aftermath. The one now is called Aftermath Blue, which is what I just showed you. So this is where you can download it. So Aftermath Blue right here, the download, you can download it for free and upgrade to that version.
Yeah.
And then you can use that with your potentiostat. So I'll just put a link to that Aftermath Blue download page.
Yeah.
So yeah, feel free to check that out.
Okay. All right. So the next question is from Wang Kailai. And actually, I remember when you asked this question a while ago. It was one of the previous questions we never got to. So thank you for reminding us about it. If we do not apply an extreme voltage for chronoamperometry, that won't be used up for redox species on the electrode surface. Does the current versus time curve still fit the Cottrell equation? The answer is yes, it will. It's not what you want, but it still will have or fit that same form. And what I want to show you actually is you can simulate this. And right now I'm using Aftermath Live. This is our simulation software. And I have this is the parameters for bulk electrolysis. Bulk electrolysis and chronoamperometry are effectively the same thing. So let's say, for example, you just have a very simple one electron transfer reaction. It's let's make it an oxidation reaction. And this oxidation reaction, let's just say that it happens at 500 millivolts. Okay. So now, and then I have, 1 millimolar of A, and it has these normal diffusion coefficients, very fast electron transfer kinetics. Now, when I do bulk electrolysis, normally you want to apply this extreme potential. So I apply like 1,000, 1 volt, 1,000 millivolts. And if I do it for like 10 seconds or something like that, and I simulate it, I get this nice current. And if you look, this has the kind of, it might be a little hard to see, but it does have this Cottrell-like behavior. This is the exponential decay of the current over time. But one thing I want to draw your attention to is that like the peak current that we're getting here is almost like a little over 9 milliamps. But when you pick a voltage that isn't as extreme, let's say you have it at the potential, and you do this, you get less. You actually get, just below 5 milliamps of current when the potential is, at, if you will, the redox potential. So the starting current will be different, but this shape is the same. The shape is still an exponential decay over time. So that will happen, but the peak current that you start with will be different. And as a result, let's say we archive this, and then we also archive, we redo this guy, simulate it, and I'm going to overlay the bulk electrolysis results. I'm going to pin it, and then if I go back, we can zoom in. You'll notice that there will be a difference. So this is when, so the curve shape is the same. The red is when I have 1 volt being applied as my step potential, and this faint pink is when I have just 500 millivolts applied. And so the shape of the curve is the same, but clearly there's an offset. There's more current in the Cottrell, for the Cottrell response, when I have a higher voltage. So the shape will be the same, but the current response will be different, which is why we always say, hey, you need to apply a much higher potential in chronoamperometry than you would for doing a Cottrell plot or something like that. Because if I went to I think if I went to like 900 or something, you'd find it actually doesn't change. It's still high enough. But it's only when I go lower, when I keep going lower, that's when I run into an issue. So so that's it. That's all I wanted to share with you. And of course, you can always use Aftermath Live. I always encourage people to use it as just to play around with the software to learn what the electrochemical response would be for a certain process. Okay, so that was Wang's question.
It's like Situ has the next question.
Yes.
I think. So good evening. Carbon nanotube glucose oxidase composite pellet gives an OCP of minus 0.45, while the same ink drop casted on a glassy carbon gives 0.1. Why? So explain the relation by way of OCP and electrochemical double layer.
Please.
Okay,
so carbon nanotube glucose oxidase. So as a composite pellet versus, well, when it says composite pellet.
Okay, so as a general thing, I'm just going to assume, for instance, that you have the same, and I say that with a heavy caveat, the same setup, which of course nothing's ever quite the same, even if you think it is for one reason or. But let's just say, for example, that you have the same electrolyte, the same counter, and the same reference electrode, and the only difference between these two situations is that in one case you have a pellet somehow integrated into your system, connected, right? And in the other case, you have the drop casted material, right? But everything else is the same, because an obvious answer is that, well, any change in the electrolyte or in the reference electrode specifically will cause a change in the open circuit potential, or can, very easily cause a change in the open circuit potential. So I'm going to assume that isn't the case for you. The only quick thing that comes to mind is that, the potential that's measured is an aggregate of anything that's in contact that has its own possible reaction. So, one possibility is that there's some foreign contaminant of some sort on your glassy carbon electrode with the drop casting process, or some other foreign contaminant. Is there a binder material present in one and not the other that could be participating or causing the voltage change? Because remember that the voltage is not the same as the current, which is to say that even a very tiny amount of material that has its own redox, reaction of some sort, regardless of its surface area, that can change the potential. Right, the amount of current you get and a very small amount of material is going to be really, really small, but its voltage, its potential, that's set by thermodynamics. That's set by the Nernst equation. And some amount of material in the pellet or the drop cast that's different, binder or again, like some foreign material, maybe you don't realize is there, could be causing a change in the open circuit potential. That the glassy carbon itself could be causing, could have some, if it's not fully covered and some small amount of the glassy carbon is exposed to the electrolyte a little bit, that could be changing the open circuit potential ever so slightly. Those are just some thoughts I have, I guess. I don't know.
Yeah, no, I agree with you. I was actually looking at the glassy carbon. You're talking about a pellet of carbon nanotubes and glucose oxidase. I'm thinking of that as like a bigger macro structural thing. But then if you have a thin film, even if it completely covers the glassy carbon electrode, the glassy carbon electrode is like the conductive medium, sort of say. So its inner potential, if you will, is just set differently. So you have glassy carbon, thin film, then solution, and that's your OCP, versus composite, which is different thing, different inner potential, solution thing, and then you have OCP, and it's minus, because that's about half a volt difference or so in the open circuit potential. So I think the inner I'm thinking the inner structure of what you're measuring is just different. So
and it's the fallacy of thinking that everything is exactly the same. Maybe the carbon nanotube glucose oxidase material is fundamentally the same between the two, but the construction of the electrode is different, such that yeah, I would expect a slightly different open circuit potential. So you know, and obviously, well, hopefully the thing you're trying to study is the faradaic, you know, the reaction of interest or whatever, and assuming that still functions in both cases, hopefully the location of the open circuit potential in both cases is not as big of an issue, for instance, provided the current and the, you know, metrics of your reaction are still relevant or measurable, right? That's what hopefully matters most.
Hopefully that answered your question. Let us know if you get a.
All right, and moving right along here, we are so many questions.
Yeah, I have so many questions.
I think NASA.
You already told Howard not to, that the PowerPoint is going to be available. So
yeah, we skipped the PowerPoint.
Yeah, Nasser.
Yeah, so newcomer in electrochemistry. How would you explain the voltage of a battery? Does the voltage determine the specific capacity of a battery, and which one determines the battery capacity, anode or cathode? Okay, so there's 3 questions here. So how would you explain the voltage of a battery? All right, let me draw some things for you. All right, so a battery. There we go. All right, so a battery. So you have a cathode and you have an anode. Okay. By convention, the cathode, this is where during discharge the reduction occurs, and the anode is during discharge where the oxidation occurs. In a typical potentiostat configuration, if you will, this is the working electrode. This is the counter and the reference. Okay. And so the voltage of the battery, the voltage of the battery, or sometimes we say E cell. These are all terms for the same thing. Okay. So however you want to call this, it's the potential of the cathode minus the potential of the anode. So that is the voltage of the battery. At all moments in time, it is the potential of the cathode minus the potential of the anode, because it's working minus reference, working minus counter, basically. Okay, so that's the first part of your question. Let me look at the next one. Does the voltage determine the specific capacity? No, it does not. And which one determines the battery capacity, anode or cathode? Okay, good. That's a good question. I'll answer this 2 ways. The first answer is a practical answer, and it is the cathode. The second answer is that it depends which one has a higher specific capacity. So I've shown this before. I'll show it again. Hopefully this will be helpful for you. I'll show you how to calculate it. I like to use carbon as the example. So the most common anode material is carbon, graphite, in some form. So what it actually is we have 6C plus Li plus an electron gives me LiC6. Okay, that's like the anode reaction. This is the charging process. So if we go this way, it's discharging. So this is charge. This is discharge, going backwards. Okay, it's not that important. All I really need here. So the capacity. So what is the capacity and the specific capacity really? So the specific capacity, it's actually the simplest possible thing. Battery people find a way to take the simplest possible quantity and make it fancy and confusing, but it's actually just the formula weight. Okay, so 6 times carbon, which is 12 grams per mole, right? Because it's a C6. 72 grams per mole of C6. So there's all I'm doing is writing something that's hopefully very obvious. There's 72 grams of C6 per mole of C6, right? This is just a formula weight. All we're going to do is take the inverse of that. 1 over 72 I draw my 7s weird. I know people have told me that. I don't care. Okay.
I think
This
it looks
is,
fine.
I just have this weird thing. I don't know why. I've always drawn the line through it for some reason. It's like
Yeah,
it's like a weird habit. I'm not sure why. Per
it's
gram.
clear it's a 7.
Is it? I hope
I
it
think
is.
it's clear.
Okay. Well, yeah, but you've known me for like 10 years.
I haven't known your 7s for 10 years though.
Oh, well,
So now your 7s are just,
welcome
like,
to the madness, my
the
friend.
madness of-
I don't know. I've had people tell me like, why do you do it that way? I'm like, I don't know. I've been doing it that way forever. It is a good question though. It's a very weird thing. Okay. Anyway, sorry. I'm getting way late. All right. So this is literally this number here will transform into the capacity. I'll show you. So this is stoichiometry for 1 mole of C6. Just look up here in this equation. We have 1 electron, right? Or 1 mole of electrons. I can't do the undo because it's going to cancel the thing.
Yeah.
1 mole of electrons. That's technically correct, right? Now, what do I want to do? You need something to convert moles of electrons. Faraday's constant. 96, 485.3 coulombs per mole of electrons, right? This right here is Faraday's constant. F. That is Faraday's constant. Okay. Okay, so this actually is the capacity. We do one more transformation here, which is to use, there is 1 hour has 3,600 seconds. This is just the number 1, cleverly written, right? 1 hour has 3,600 seconds. So if I do that math out, let me get my handy dandy calculator. I know you can't see it because you're looking at PowerPoint, but 1/72 times 1, right? Times 9645.3 divided by 3,600. That equals 372. I'm doing a quick conversion. So milliamps hours per gram. That right there. So this is the calculation of carbon's specific capacity. This is the number. You'll see this in papers everywhere. 372 milliamp hours per gram. That's how it's calculated right there. Okay. So which one determines the capacity of the battery, right? Well, if I have 1 gram of carbon, it has 372 milliamp hours of capacity, right? But if my cathode, as is typically the case, let's say my cathode, right, has 100, there's a 7 again, 170 milliamp hours per gram capacity. Well, if I have 1 gram of my cathode and 1 gram of my anode, my cathode can give me 170. My anode can give me 372. Well, I'm only going to get 170 because the lower, that's the rate limiting one, right? So I could use 2 grams of my cathode. That's 340. Let's just say 2.5 grams, whatever. I could match up the mass. Do you see? Hopefully you see what I mean. If I have 1 gram cathode, 1 gram anode, whatever the lower number is going to be the determining factor. And so the reason why I said the answer to your question, which one determines the capacity of the battery, it's usually the cathode because cathodes intrinsically have less specific capacity than anodes do. Anodes have more. So one of the other things that's a consequence of that is that in commercial batteries, the cathode is thicker than the anode. You have to use more mass of the cathode to equal the capacity of the anode. Whichever one is the smaller number is what limits the capacity of your battery. Okay. So Nasser, follow up if you need any clarification on some of those things. We're going to move on, but hopefully that kind of gives a little summary of batteries and some of that mathematics and how that's done. So
yeah. The next question, I guess maybe it's a comment. I don't know how much to answer it. It's from Focus on My Dreams and Carrier. I want to do theoretical studies in my research. I am a UPing undergrad researcher. Where should I focus to get improving in my research? So this question is very general. There are so many areas of research, both theoretical and kind of practical. people usually focus on like a specific thing, like, lithium ion batteries or electrolyte or a fuel or a specific kind of fuel cell or a specific kind of catalyst. That's usually what people do. As an undergraduate researcher, my recommendation is to find professors at your university or college who are doing electrochemistry research and just get hands-on experience. I don't know if you have anything to add.
That is the only answer I would say, actually, is exactly what you just said.
Okay.
Especially as an undergraduate, most likely, my guess is if you're an undergraduate and you're getting into research, it's either extracurricular or perhaps you have a paid internship or an unpaid internship. Or in other words, it's when you're a PhD student, you're at the stage where it's really imperative that you get better, learn how to do it, figure out your project over time. It takes time. And to a certain extent, the answer for a graduate student is similar: get in the lab and do it, right? But it is incumbent on you as a graduate student. You have to read a lot of literature. Shamelessly, our YouTube channel, this events like this, webinars and workshops that Pine does, we try to fill in those gaps as best we can in a lot of cases to help give hands-on kinds of advice to people. There's textbooks, and the scientific literature is always good to consult with. But as an undergraduate, really, it's like get in the lab, just try stuff, right? Find yourself a professor who's willing to let you try to join a project and just do a few simple tasks. It'll probably be some synthesis of materials with a recipe that's a known thing, but you'll get your hands on putting some chemicals together and doing some processes to make a catalyst, make a material, do some, if it's electrochemistry, obviously, using a potentiostat to do some very simple cyclic voltammetry or some amperometry or some simple tests with a well-known system. Just get in the lab and just do stuff. Like it's such a simple answer, and it feels like a dodge, I guess, but it really isn't. It's like, it's just start doing stuff. Don't worry so much about whether it's good or bad, right or wrong. It's going to be wrong. That's research.
Yeah.
It's going to be wrong for a long time, even if you're a graduate student. That's part of the process. You're going to do stuff wrong. You're going to get weird results. You have to do that to learn how to do it right. Like, almost nobody has a story about like, well, I just got into graduate student and everything just came up aces. All of my experiments worked and I graduated in 95 minutes with 17 publications. Like, nobody has a story like that, right? I had a great time in graduate school, but I failed miserably for like 2.5 years consecutively. It was an incredible streak, like more impressive than Michael Jordan's streak of 2 3-peats. Like, my failure streak was, it was good. So, so don't worry about it, right? Just, you need to find a professor and or like set of graduate students or mentors, right? In a laboratory that are going to let you just get in and just learn, play with stuff. You're gonna, you can't be afraid to fail. You can't be afraid to get your hands dirty, literally and sort of figuratively here. So yeah, that's great advice.
Let's see. The next
Abderrahman.
Abderrahman is asking, hello, I got the transference plot of my electrolyte. However, instead of a regular decrease, as in theory, there's a bit of a dip, and then the curve regained its trend. Is the result still valid for the transference number calculation?
What's the transference plot?
Yeah,
so I've gone over this. It's called the Bruce and Dunn method. I've talked about this a couple of times.
Bruce Vincent.
Bruce Vincent, excuse me. Yeah, I'm confusing the Dunn method.
Yeah.
Transfer, but I'm not aware of a transference.
Yeah.
I mean, so to reiterate a little bit, the Bruce Vincent. That's
Bruce,
it. Yeah. Again, I haven't done this personally, but I've read through the paper and I looked at a previous, someone asked this 1 or 2 weeks ago.
Yeah.
And then I found, and I rewatched my own answer that I had then, probably 6 months ago at this point, researched myself a little bit. And as best I can understand it, effectively you do chronoamperometry, impedance, and chronoamperometry in sort of sequential kinds of steps, right? And you're finding resistance and current, like the steady state current, basically, at a couple of different voltages. And there's an equation. It's a very simple equation that calculates the transference number. So I guess what I don't totally know, Abderrahman, is you say, I got the transference plot.
Yeah.
Do you just mean like an amperometry plot and you're saying it's doing something strange? Like, I don't know precisely what a transference plot is definitionally.
Yeah. It's
Current,
like
like a current versus time, he says. Okay. Like a current versus time. So yeah, so you're talking about like an amperometry plot. So you're saying instead of a regular decrease, as in theory, there's a
Oh,
dip and then it regain. Okay. So what you're seeing, I'm guessing, and you can sort of comment if you wish.
yeah. It's like you have a little dip or something.
Yeah. So like,
maybe.
yeah, like, sorry, I'll start a new slide.
Yeah.
All this battery nonsense. Yeah. So like, if you're talking about like, and then maybe it like, I don't know, moved, instead of dipping down and just getting some flat, and then this is, you just take a current somewhere, that's your steady state current, whatever. If it like,
Mhm.
if it bumped up or did something like that. Right. I'm guessing that's what you're talking about, but effectively your curve, IO and I of the state. Yeah. So it's like not behaving properly. It's swimming around, so to speak. It's not looking properly. Well, frankly, it might be your selection. So my understanding, again, which is somewhat limited to be perfectly honest, but the Bruce and Vincent method involves a selection of a couple of different potentials, I believe, to get those current versus time plots. It may be that the potentials you've selected are not the best. It could be that you've selected a potential where there's some transient, some unsteady faradaic process happening such that you're not getting the normal IT, decay steady. It's not reaching steady state. So you might choose different potentials that's my quick possible answer to you is select a different potential. Because as I understand it, the way that this method works is it just requires two different potentials. And then you're measuring the impedance and the steady state current at each of those, and then those voltages work their way into the equation. But there's no requirement for what those voltages necessarily need to be, as far as I'm aware. So perhaps pick different potentials and try again. See if you find two different potentials, for instance, where it's they are better at reaching a steady state, right?
Mhm.
It might be because if it's not reaching a steady state, it's not following the Cottrell equation. There's some unsteady, it's like definitionally you can't use this method if it's not steady
Yeah.
state, right? It has to reach a steady state. So perhaps I don't know 100% why it's not reaching steady state, but it isn't based on the behavior you're observing. So try adjusting the potential. Maybe you'll find a better one, I guess. And Nicholas, you apparently win because you had 3 years of failure. So yes, you are first, but I'm a close second. A close second. It was like right around 2.5 years, and then my last 2 years were excellent, all success. But yeah, you just got me beat. So I'm sorry, I guess. Okay.
Okay. Moving on.
There was a bit about the Nicholas had to follow up, but I think
Yeah.
OCP as the almost kinetic and
Yeah.
partial potential zero charge, more like a thermodynamic. I mean, that's kind of I don't know. I guess we won't elaborate too much more on that because you kind of showed a good summary, I guess. But anyway. Okay, then we talked about the turnover.
Yeah,
frequency.
turnover frequency.
So
Mosin, I think, is next.
Okay.
Mosin Cyanide is saying, "Hello there. How are you guys? I wanted to ask how to perform a circuit fitting of EIS, then calculate the resistance parameters from there, like RS, RCT. I use
Z-SimWin.
Z-SimWin.
It's I think it's Princeton Applied Research's.
Oh, okay.
Z-SimWin.
Yeah.
So we can't show you how to do it in that software specifically. That's not our company's software. I can show you how to calculate it in our software.
Yeah.
Which is Aftermath Blue here. So let me just make a circuit simulation, for instance. So if you're trying to find the charge transfer resistance and the solution resistance, again, I don't know how Z-SimWin works. It's not my company's software. I don't have it, obviously, so can't help you with that specifically. But if you have a Nyquist plot, for instance, the solution resistance, you can see the 0 here on the left side of this axis. The solution resistance is the distance on the Nyquist plot that everything starts. You see how I'm moving this value of R1 or the R0 or whatever, RU, there's different names for it. Left and right, that just moves the whole Nyquist plot left and right. So to calculate RS, basically, you actually, it ends up being just the intercept on the left side of the Nyquist plot, where the set, like if you have a semicircle, it's usually the case, right? Where everything starts. It's the left x-axis intercept. And then the charge transfer resistance is the width of the semicircle, very simply. Now, a circuit fitting algorithm probably is Z-Simple has that. Our software does too. This is just a simulation. I'm not circuit fitting any raw data per se. I could show you that, but I won't get too heavy into that just for interest of time. But you can see as I change the value from small to large, the semicircle grows or shrinks. So very simply, the resistances are actually quite easy to find on a Nyquist plot. The solution resistance is the left intercept, and then the width of your semicircle is equivalent to the charge transfer resistance. So that's how you get those directly from a Nyquist plot.
Mm-hmm. All right, moving on. Tadios has a question. How to translate Tafel slope in proper way? I doubt the quantitative interpretation, but I don't know. What do you think? And I guess kind of continue, he says, I use a wider potential window for CV between 0.2 and 0.8, but I still use the non-faradaic region to calculate CDL, the middle point at 0.05577. Is that okay? I think we may have to see I think we have to probably see the voltammogram specifically to answer.
With these specific numbers that I have to see your data to know, is that the right value to use and everything.
Yeah.
Strictly speaking, you can use all of the voltages to make a Tafel plot. The question is whether it's valid and relevant.
Mm-hmm.
Technically speaking, the Tafel equation, and therefore the Tafel plot, is a direct manipulation of the Butler-Volmer equation, which is an equation that relates kinetic current to overpotential. The key there is kinetic. It's not current, it's kinetic current. So it, to your first comment, how to translate the Tafel slope in a proper way. In some sense, it's make sure that the Tafel slope that you are measuring is even appropriate in the first place. Because the translation, so to speak, of the Tafel slope depends on whether it's even appropriate to make the Tafel slope at all. Okay, and I'll show you what I mean because I have a slide on this. Let me find that slide for you, and I'll show you where the Tafel slope comes from, the Tafel equation. I have that here. So the Tafel equation comes from the Butler-Volmer equation, which is this equation right here. Okay, this is the Butler-Volmer equation. What we do is we get rid of one of these terms, but goodbye. Okay, this right here is the Tafel equation. It's half of the Butler-Volmer equation. And what we do is we solve for the overpotential. So we solve for eta here. Just do a manipulation, take the natural log of both sides, or the log base 10 of both sides, and we solve for eta, and then we get what's known as the Tafel equation, where we can get the Tafel slope. The Tafel slope is all of this stuff in the green box, RT over alpha NF log of E. This is just a number, okay? So, and this comes from the plot of the overpotential versus the log of the, again, kinetic current. So again, I'll harp on this point until I'm blue in the face and I'm rolling over in my grave someday. Don't make a Tafel plot unless you know you have kinetic current. It's a common mistake people make is they take any voltammetry data, turn it into a Tafel plot, and assume it's valid. That is not an appropriate thing to do in a lot of cases. However, if you are confident that your current is 100% kinetic current, then the interpretation or translation or whatever sort of terminology you want to use is usually in terms of N. A lot of times the Tafel slope equates to a way in which to interrogate the number of electrons of your reaction that's occurring, because it is a factor of 120. So in a perfect irreversible one electron transfer process, the numerically this Tafel slope R times T at room temperature, alpha with a perfectly symmetrical energy barrier, and one electron transferred. The Tafel slope is 118, basically 120 millivolts per decade of current. So this number shows up a lot. That's where this comes from. It's the calculation of a sort of ideal Tafel slope. So a lot of times what you see as far as what does my Tafel slope mean is it's usually a multiple of 120 or lower. So it's 120, that means n equals 1. If it's 60, n is 2. Right, n is 4, it's 30. If it's 40, if it's 3. So there's, as a side note, that's also a tricky thing because technically speaking, this equation has the assumption that it's a one electron irreversible. And so we're sort of already disobeying to a certain extent when we have multiple electrons transferred. It's a bit of a catch-22, but I'll leave that there for now. But generally speaking, what you're looking at is somewhere around 120 or lower, usually. And we're using that as a way to interrogate how many electrons are being transferred, or something about the symmetry barrier, which is not often changing too much, but I guess it's possible. Most of the time, things like oxygen reduction reaction, people are looking at how close to 4 can I get it, because that's the ideal number of electrons transferred and things like that. So there you go. So that's kind of the meaning of interrogation from the Tafel slope, I guess. Feel free to comment if you need a follow-up. So,
all right. So I think the next question is from, because I have to scroll down a bit. I think it's from Ramsa. Ramsa is asking, how does the potentiostat actually measure the migration current? And kind of, I guess, maybe somewhat of a follow-up, he's asking, how does the supporting electrolyte minimize the migration current? So the potentiostat, to kind of clarify, migration is the movement of ions and or mass transport associated with an electric field. A potentiostat just measures the current. It's the total current of the system. It can contain faradaic, non-faradaic current associated with diffusion, current associated with migration, all kinds of things. It's just the total current. It's usually up to the researcher to deconvolute what that current is associated with. So migration current is, let's see. So actually, so it just measures the current, and there may be a factor of the current that is associated with migration. It's just measuring the total current. So migration current itself is not necessarily a thing, if you will. But I think more importantly, what you're asking is in the second part of your questions, how does the supporting electrolyte minimize the migration current? And I think what you're getting after here is the fact that when you add supporting electrolyte to your electrochemical system, you minimize migration, which is the movement of molecules in association with an electric field. So this happens in kind of several ways. When you add supporting electrolyte to your solution, you make the solution more conductive. And generally speaking, we think about conductors like a solid piece of metal or even glassy carbon as things where there is no electric field inside of a perfect conductor. And so as you add more electrolyte, there is no electric field. And the reason why there's no electric field is because there's always a level of charge balance very easily, or it's very easy for ions to shield the electric field from another ion. So every bit of charge in your, kind of atomically, if you will, in your solution has an electric field. But because it's next to other supporting electrolyte or other charged ions, that field is kind of negated or it's shielded, sort of say. So in that case, the electric field, the reason why you have a small electric field or a tiny electric field, if you will, or no electric field in conductors is because charge is kind of perfectly balanced within a conductor. So the field is not there. I hope that kind of makes sense. If you need more clarification on that, please let us know. Otherwise, we'll just kind of continue on with the rest of the questions.
And I think Sidhu is the next question, which is how does the electrical double layer affect the OCP?
How does ionic strength?
And then how does ionic strength of the electrolyte affect the electrical double layer? So first of all, it's somewhat of a catch-22. The OCP or the voltage, anything doesn't even exist without the presence of the double layer. It has to, the double layer sets up before anything can even physically happen. So it's maybe a bit of a complicated thing to really get into. But I don't know that the electrical, I don't know if this is the right thing to say. I don't know if the electrical double layer affects the open circuit potential. I don't know that that's,
so it's
that's the right coupling of concepts. You know what I mean?
Yeah. So I talked about this a little earlier. I'll just go back to this equation where we're talking about the potential of zero charge. So this part right here, I'll just highlight. Actually, no, it's hard to highlight. I'll just yeah. I'll use blue because I have a lot of red and black here. So this here, this part, this is the electrical double layer. So the fact that there is a potential difference between the inner potential of your electrode and the solution potential sets up the potential. Like this is the electrical double layer. Like this right here, this potential difference, the potential of your working electrode is the electrochemical or the electrical double layer potential. So that's just what it is. When you change, and so the open circuit potential, if you will, is really the difference between these two potentials, which is the potential of the double layer, minus the reference electrode potential. If you're in a 3 electrode configuration, and this is the potential where no current is flowing. So when you have a voltmeter here, that's what you're looking at. That's what you're measuring. When you change this by using a potentiostat to say, oh, I'm applying 1 volt or some other thing, you're really just changing this value here. And this is that's what you're able to get when you're doing a cyclic voltammetry experiment. You're really just changing this number. But this is what it is. The electrical double layer is the difference between these guys, and the OCP is the difference between this whole thing when I equals 0. That's the
I think that's the thing
relationship.
that's the difference between you and me being chemistry and more like engineering.
Uh-huh.
Because what you just described is the right way to answer it, which is the double layer is the phi M1 minus phi S.
Yeah.
That's the potential of double layer.
Yeah.
And the OCP involves that as per the equation
As
that you
per
have
the
there.
equation.
I'm going to hide the questions.
Oh, yeah.
Basically, the potential of the double layer, so effectively minus the reference electrode, is the OCP.
Yeah.
Right. But when I'm thinking about it, my answer is kind of like, well, it doesn't really matter because you can only affect phi M anyway.
Yeah, that's
it's like
you can only affect phi M anyway.
It does affect the OCP, but your ability to control is specifically not related to the EDL necessarily. Like as far as a potential, as far as the OCP, you can control the phi M. You can't control the phi M minus phi S. That's going to be whatever it is.
Yeah.
That's why I'm sort of like, I don't know.
Yeah. The phi S is just you can't control this.
It is there. Yeah. But the other part of the question, I think, how does the ionic strength of the electrolyte affect the electrical double layer? So, if you have a stronger electrolyte, you're going to have a tighter double layer, basically.
Yeah,
right. So, stronger electrolyte means the electrical double layer is going to be tighter. It's going to be close. Like it's going to be
more compact.
Yeah, exactly, more compact because it's a stronger. It's a higher capacitance of capacitor. Going the other direction, a low ionic strength, like a dilute electrolyte,
Mhm.
will have a bigger, less tight double layer, which it's more spread out. And that you can think about that as it's a capacitor where there's greater distance between the plates, something like that,
Mhm.
which means it has a lower capacitance, because the capacitance of a capacitor in terms of farads or whatever
Mhm.
is inversely related to the distance or the tightness, right? So the capacitance being greater because of a greater ionic strength leads to a tighter capacitance, which means so it has a bigger capacitance, which means it has a lower impedance
Mhm.
because it's inversely related.
Right. Yeah. Those are inversely related.
Yeah.
Hopefully that makes sense, Sidhu. Of course, if you have more questions, we can
Follow up.
we can follow up. Yeah.
But Nantu Das has the next question.
Yes.
How to set up a 3-electrode system using glassy carbon working, silver silver chloride reference, platinum wire as a counter to achieve minimum IR drop. Which reference is better to use with Vicor frit or normal porous frit with a Lugin capillary? In general, reducing the IR drop means getting the reference in working electrodes relatively close. There's some sort of rule of thumb, if you will, that something like the distance between working and reference should be something like 3 to 4 or 2 to 3 distance
de-
of the diameter.
Yeah, like one or two.
Yeah, one or
just
two.
minimum.
Okay, yeah, something like that, right? If it's too close, you get weird polarization effects, or what is it?
You disrupt
field effects.
you disrupt diffusion.
Okay,
Because
that's
the if the
it's a diffusion
area of
thing.
the electrode's really big, you're thinking about diffusion kind of planar to
Right.
that.
Mhm.
And if the reference electrode's here, like beyond the diameter, it's going to disturb how the molecules diffuse.
I thought it was also a field. Is there a field effect too? It's just a diffusional thing. Maybe it's just a diffusional thing.
I mean, it may be a field effect as well.
I'm not sure.
That could also be. The
It might
case
be
as well.
both, but definitely the diffusional thing makes a difference. But
Yeah.
effectively, if you have like a 5 millimeter diameter, you could say, as a general rule, somewhere between 5 and 10 millimeters away,
Yeah.
if possible, would be
Yeah,
great.
would be safe,
It's not always possible, but if you have a concentrated enough electrolyte, you'd be all right, basically. And then let's see, reference Vicor frit or normal porous frit. Well, Vicor frit is a normal porous frit. Those are.
Yeah.
I'm not sure if you're using something different, or a Lugin capillary. A Lugin capillary is useful in some systems where you need to isolate the reference electrode physically from the electrolyte. Another name for that could be a salt bridge. It's sort of a similar phenomenon, but the Lugin capillary is meant to direct the ionic path from the reference directly to the working electrode. In my observation and experience, the use of a Lugin capillary is not always necessary, especially if your electrolyte concentration is strong enough. If you have like half molar salt in aqueous solution, a Lugin capillary is irrelevant. It just is. It's my opinion. I'm sticking to it. But in theory, if you have some dilute solution or you have a reference electrode that can't be exposed to some electrolyte, you can put a Lugin capillary and then a different electrolyte to sort of try to isolate the solutions. Things like that can be useful. Be careful in terms of using too many frits. Just in general, people use double junction reference electrodes and things like that, and that's can work just fine. But once you start getting to 5 tens or higher of kiloohms of impedance with multiple frits that can become blocked, you can have a real problem on your hands. If there's too much impedance associated with the pathway between working and reference, you can have some real trouble, especially if you're doing impedance experiments. So you can use frits. You can certainly use frits. A lot of times they're necessary, and most reference electrodes have frits for a good reason. But just be careful. Make sure they're not blocked, not clogged, things like that, because it can be severely detrimental to your experiment. So
nice.
Looks like Ramsa had a follow-up, I guess.
Yeah, we can go to Ramsa's. He has 2 things he wants to know. Then what about current carried by ions of the supporting electrolyte? And that would mean there would be contribution of migration current from ions of supporting electrolyte when the ions of supporting electrolyte migrate um, in the influence of the electric field. Yes. So that happens, and yes, the current carried by ions. I still think that when like an ion moves, it's like, because the whole thing is a circuit, right? So let me like, how does a potentiostat measure it? Was your first question. So I think about if I have an electrode and I have a voltmeter and I have another electrode, and then this is all in solution here. Current is flowing. So let's say electrons. Let's say it's like a oxidation reaction. The molecule loses an electron to here. The electron is now moving through here. The electron's got to be moving this way, and then you have a reduction reaction, right? So that's one thing. If ions are moving, it sounds like you're looking at more like transference number, which is to say how much of the current is passed by either the negative. I kind of drew those backwards in a way. The positive ion is smaller than the negative ion. That should be this way, generally speaking. But these also have to move too. Like this ion moves and that ion moves. And the electron, of course, can move very fast, but ions move a lot slower. So the limit, sort of say, in terms of this motion, which is what measures the voltage, this guy has to move through here for a voltage to be measured, or current to be measured. Sorry, for current to be measured, and voltage for that matter. So it is when these ions move that you end up getting a current response, and it's because you're effectively moving an electron through this voltmeter that is giving you a response. Now, there are still things about the nature of like the transference number that I don't understand. But to your other question about like things like the formation of the electrical double layer, well, the way I think about it, at least, is that you do have ions moving to the surface in response to forming the double layer. So like plus charge here. I'll just do pluses here. And you do have a current associated with it. So we know from cyclic voltammetry that when you have these voltammograms, you can get non-faradaic charging current, because like if 0 is here, there's a current associated with the charging, the movement of the ions here, and the flow of negative, either holes or electrons towards the electrode. And the way I think about it is it's the movement of these guys here that allows the electron to move in the voltmeter to give you a current. So that's how I think about it. And then let's see. So wouldn't there be contribution of the ion? Yeah. So this is let's see. So when the ions of supporting migrate in the influence of the electric field, wouldn't there be a contribution of migration current from ions of the supporting electrolyte?
The supporting electrolyte migration is the canceling out factor, effectively, right? I mean, I think he's like having a strong enough supporting electrolyte negates migration.
Yeah, and to be clear, there is an electric field at the electrode surface, and it's very thin, right? Like I've drawn these like phi s and then phi m, and there's an electric field. There's an electric field at the electrode surface, but this whole thing is like max 20 angstroms.
Oh, not even.
Yeah, maximum, right? So it's very thin. So whenever people say like, oh, we don't consider migration as a contribution of the current, it's because once this is established it's very thin compared to the rest of the bulk solution. And sometimes it's like, 10, right? 10 angstroms. So we say that like mass transport, the association of the field, current associated with the field, is very low because it's really, really tiny. The thickness of the diffuse layer, if you will, the diffuse layer thickness. Yeah, I think that's
Yeah.
generally how I think about it. You have a field. It's very small.
Morpholino just commented is correct here. This is just a good summary, I guess, of what you're talking about here. Migration in a reasonably concentrated solution, let's say 0.1 molar, probably even lower than that, but 0.1 molar solution is not relevant, only very close to the electrode surface, as you said. It's 1 or 2 nanometers or something, 10 angstroms, whatever.
Yes.
It's negligible, basically. You want no migration, only to have fixed law of current apply. Exactly, fixed law has a migration term, and we neglect it for this very reason. And then he follows up saying the Debye length is what determines how far the electrode influence is, quote unquote, felt in the solution.
Yes.
So,
yeah,
and that's very it's a very small amount here. So I think maybe what the general thing here is you're confusing or conflating, I guess, that the fact that there's the movement of ions, whether it's supporting electrolyte or otherwise, to complete the circuit, so to speak, to create a net neutral movement of charge or current, basically, right? That's not the same, I guess, as saying, oh, there's a migration that's accounted for. That's just the electrolyte movement counteracting and existing in enough concentration to complete the circuit is what makes all of this possible. It's not its own contribution for migration. Something like that. So, but it's a good question.
There is the question about like how the transference number is calculated, because the transference number is all about just the electrolyte itself, and there's a current and EIS component to that. That's something to look a little bit more into. But these are like CV experiments.
Okay, so let's see, like world of chemistry. There's a couple of questions. I want to ask simple questions: how to calculate OER and HER from LSVs, and then.
So that one was actually, I checked, that was retracted on YouTube. The clarification of the question is,
I see.
I'm confused about how to calculate overpotential for HER and OER.
Okay.
Not just how to calculate OER and HER.
Oh, I see. Okay. So it's actually quite simple. I'll show you. So overpotential is defined as the difference in the applied potential and the thermodynamic E0, for example. So the oxygen evolution reaction, I'm going to assume for acidic media, just for simplicity here, is anti-stoichiometry later. It's 2 waters, I think. 2 water gives you 2H plus an oxygen plus. No, not H2, H plus. Sorry, 4. I can't undo. So sorry. Of course, I'm human. I make mistakes here. 4H plus plus oxygen plus 4 electrons, right? Okay.
Yeah, there you go.
Yeah, 4 H's and 2 O's and 4 electrons. Okay, perfect. The E0 of this reaction is 1.23. I've drawn it as an oxidation. I should have drawn it as a reduction. That's my fault. But anyway, this is the E0. Okay. So the overpotential, which is the Greek letter eta, looks like an N kind of, is defined as the potential that you have applied minus E0. So it's really just simple arithmetic. It's just moving the potential axis. So for example, if I apply 1.53 volts, my overpotential is 1.53 minus 1.23, right? My overpotential is I'll just convert it, 300 millivolts. Okay, so that's my overpotential. So what that's saying is that I have applied 300 millivolts of potential above the standard thermodynamic potential for which OER occurs, basically. And so it's like a driving force. It's, in the absence of other things, of course, like diffusion and other stuff that we know, you have a higher over potential, you're driving the reaction more and more, basically. And so without doing more craziness, the hydrogen evolution reaction is a similar thing. It's actually much easier. Watch me screw it up. We have two protons, plus 2 electrons gives me hydrogen gas. And this one's a reduction, doesn't really matter either way. The E0 is by definition 0, right? 0 volts. So this is like the reference reaction for electrochemistry. And so the same thing applies, right? If because it's a reduction reaction, we would want to go negative. We would want to apply a negative overpotential. So if we apply E is equal to minus 0.5 volts. You could see this either way. Sometimes you'll say overpotential is minus 0.5 volts, or you'd say your overpotential is 500. You would just say 500. They might neglect the minus sign. It's sort of implied. It depends on where you read. Sometimes people will just say 500 millivolts of overpotential, but if it's a reduction reaction, it's going in the negative direction. But technically speaking, the correct way is to say it's a minus 500 millivolts or minus 0.5 volts of overpotential. So again, it's just how far away from the standard or from the thermodynamic potential are you at, which is a way of saying how much you're driving the reaction, so to speak. Because kinetically, your current will be proportionate to your overpotential.
Mm-hmm.
Let's see, do we have a few more? What's
yeah, we have Luna is next.
Okay.
I don't know how to answer this question, actually. Can you explain the method of measuring the stability of the catalyst and if there is a difference between CP and CV in electrode deposition if I was using glassy carbon electrode with a 3-electrode system? Actually, I think for measuring the stability, some people will perform either a chronoamperometry or usually a chronoamperometry experiment of their catalyst, and then they'll see just how long does it last before the current really starts to go down. So they stir it, they making sure it's electrolyzing things, and they just see like, oh, it lasted for so many hours, or it or they do CV over a wide potential range to see over what stability or what potential window can they perform voltammetry on the catalyst to see how stable it is.
Yeah, you're literally just doing CV over and over again.
Yeah,
like 1,000 times or 10,000 times or 90 billion times. Right? I mean, that's quite as simple as a method of stability. And usually you're just looking for you look for a benchmark, or you make your own benchmark. Like I've got one reversible peak, fine. Right. And you just scan over and over and over and over and over and over again. And after like 1,000 cycles, it's not, the peak height is not as high, or the peaks are separating a little because it's losing, the catalyst is not as reversible anymore. It's deactivating or something's happening. You're just looking for the CV to change.
Yeah.
And then you'll have to come up with your own metrics for how much change is bad, good. There's a lot of answers to that. I can't really say for sure. But those are just some methods. I don't really know chronopotentiometry is used quite as often. To be honest, it's probably not as wise, because if it starts to deactivate, you might get a runaway potential and you might damage your whole electrode. Probably chronoamperometry or cyclic voltammetry are a little better, unless you're talking about battery materials. Then it's chronopotentiometry is just galvanostatic charge discharge, in which case you're just charging up, charging down, charging up. You're seeing how long it takes to hit your voltage cutoffs, and that's a different situation. But with a glassy carbon electrode and a 3-electrode system, I don't think that's exactly what you're referring to. So. It's just doing CV over and over again, seeing how it changes, basically.
I think that's it. There's one question from Shobla But you answered this question earlier.
Yeah, the specific well, it was I don't know if it's I did
specific
capacity.
capacitance or
I showed how to do the capacity of a battery material. So
okay.
Shoba, I don't know if this is the same thing. I showed how to calculate, for instance, like the specific capacity of carbon in an anode is 372 milliamp hours per gram. I showed how to calculate that. I don't know if that's what you mean. Specific capacitance is a little different.
Oh yeah. Okay.
If it's like farads per
per gram
meter,
or something
per
like
square
that.
meter or per gram.
Oh, okay.
I mean, well, the short answer, I guess, is impedance, right?
Yeah.
The doing impedance on a material and then getting the capacitance, as part of your circuit fit, and then dividing by the surface area that is there, or a mass that is there. That's really the simplest way, I think, to get that, to be honest. Or doing a cyclic voltammogram in a non-faradaic region, you have an envelope. I is equal to C times the scan rate. So if you have a current of a flat CV, and you divide by the scan rate, that's the capacitance. It's pretty simple, right? Usually we do different scan rates and kind of get some average value of capacitance or whatever, and then just divide by the surface area or the mass. So that's usually just a couple of quick ways to do it, I guess. Sorry, we're getting a little to the end here.
Yeah.
FYZ Football has been a fan since 2012. We haven't been doing this live stream since 2012, so I'm not sure what you're a fan of, but I appreciate it. Let's see. I guess must shake as the last. Let me see if I can. What does an intersection mean in a CV graph? I have a graph where the left and right vertices of your duct shape intersect thereafter another cathodic and anodic peak. Yeah, that's it's like a crossover.
Oh, crossing over.
Crossover phenomenon does happen sometimes. Let me think. This is a weird phenomenon. I actually don't have a good grasp of this one.
You get a little bit more current that comes off. It's like the current doesn't continue to go down; it goes up, or something like that.
Or it's just like it's like a reduction reaction is occurring at a greater rate than the oxidation. So even though you're going back, you're going back like in an oxidation way, you're still reducing because you're at a negative potential.
Yes.
And it's still occurring. And it's just, I think that sometimes I don't have a good grasp of this, to be perfectly honest. And I've read literature about it over the years, and I feel like it's always a little confusing, and people are trying. I feel like my impression, and not like I have a better explanation. So I'm not saying like, well, I know the answer and people are dumb. It's like, I think my impression is that a lot of researchers are like trying to figure out a way to rationalize it and not maybe 100% certain. Or there's, or it's a little odd of a phenomenon, or it's specific to one system, because it doesn't happen in all systems. But I do think that this sort of crossing over intersection sort of thing, when it happens, is something that is we can put too much weight on where it crosses exactly. Like, it's just a phenomenon of what's measured at that moment. Like, I don't know that you want to put weight into, for example, like, oh, where it crosses over, like this voltage, the voltage at which it crosses, going one direction or the other, means something necessarily. Like, I don't know that that's the case. It's just happenstance. It depends on your scan rate. It depends on stuff like that. So it could depend on the limit. If you don't go, maybe you're not going negative enough. And like, if sometimes I've seen what'll happen. I know you talked about it with a duct, so maybe what I'm about to draw isn't precisely what you're referring to, but like, sometimes I've seen where, you scan negatively, and then it's like when you go backwards, it like does that. Right. And so it's like it crosses over here, because it's like sometimes you go negative and then you expect it to go back like that. But if it doesn't, sometimes you'll have something like that happen. Like, it can happen. And I don't know. Yeah. I feel like at times in my career, I've had somewhat of a grasp of this. And then it's just like, as a scientist, I find myself having a hard time, like, The other one that I have a hard time
Mhm.
sometimes
Yeah.
conceptualizing is the hysteresis.
Yeah.
It's another phenomenon with sometimes with batteries and with RDE. Sometimes there's a difference on the way down and the way up when you're
Mhm.
rotating, slight difference, and there's a hysteresis. And it's like sometimes when people say it's
Oh.
it's the IR drop, or it's a little bit of this, or like it's a weird
Oh, yeah.
phenomenon, and I have a hard time. It's one of those. It's like the inductive loop. It's like a lot of these things where like there's a lot of like explanations that are just sort of thrown in the literature for these phenomena. And I just feel in many ways where it's become a thing where people just like, oh, these are the answers. These are the stock answers. Like it's one of these things.
Oh, yeah.
We're not 100% sure.
Yeah.
That's sort of my
That's
feeling about
that's
it. I know
true.
it's kind of a cop out. I don't want to just say for sure because I don't know if I know 100% for sure. It's an odd phenomenon.
Yeah. Yeah. I
Mhm.
agree. I don't know exactly for sure. I will say the hysteresis for RDE sometimes it's sometimes like if you scan too quickly because you are scanning when you're doing RDE. If you scan a little bit too fast, it won't exactly overlap over the initial, um, you know, LSV basically at
Yeah.
that time. Um,
I want to answer Elijah's question because I think he called.
oh, we called.
Um,
Yeah.
I spoke with you, Elijah, I think yesterday, perhaps.
Hmm.
And he purchased a circuit fit license.
Yeah.
I just want to clarify for you your question. Here it is. Sorry, I just have to find the circuit. So your question was, yeah, thank you for the aftermath blue circuit fitting.
Mhm.
So you did Kramer's Kronig and you don't get an electrochemical equivalent circuit. Is there a way to get it from Kramer's Kronig? No. And there's a reason for that. It's not, that's not part of Kramer's Kronig. Kramer's Kronig is a diagnostic with which to get an error statistic and determine how close to your data is it valid, right? Is it valid, yes or no? And it's a bit subjective because you're looking at how low the chi-squared is and how closely the experiment fits. But it is not appropriate or necessary to get an equivalent circuit. And in fact, it's not relevant. And the reason is that this Kramer's Kronig method fits this circuit, this exact one right here. It's a resistor, a capacitor, and an inductor, as well as a semi-infinite number of RCs. What our program, our software actually does is it iterates automatically. When you click Kramer's Kronig, it fits your data with an R, a C, an L, and one RC, one R, like one void element, Randall's or void element, right? And then it does 2, and then 3, and then 4, and then 5, and then up to the number of data points you have. Basically, you can't overspec. You can't do 100 if you have 50 data points, right? But it does up to the number of variables for the number of data points you have. And then of all of those fits, it finds the one that has the lowest error. That's the value it gives you. Okay. Now, what you might be asking yourself is what are the values of that R, C, L, and each RC, and how many of those void elements there are? That is not data that we provide. And it's frankly not necessary because the use of an equivalent circuit is modeling of your electrode, the modeling the behavior and the phenomena occurring on the electrode surface. Kramer's Kronig is not doing that. The equivalent circuit that the Kramer's Kronig settles on, however many of those R's and C's, that is correlated with the lowest error, represents the best possible mathematical fit, not equivalent circuit phenomenon. It's just mathematics. It's all it's doing. It's a minimization of mathematics. It's just finding that. It means nothing. There are not 47 different charge transfer processes happening on your electrode surface such that you need the value of each R and C for all of those 47. I'm just making up a number, right? But void elements that it used. That isn't what's needed. That isn't that equivalent circuit, so to speak, isn't really available or necessary. So we don't provide that, and that isn't isn't the right question, I guess, so to speak, right? So I hope that's clear. I hope I've kind of clarified that for you. The Kramer's Kronig is really used to get the error statistic and a visual verification that your data matches pretty well, to tell you that you should proceed with the circuit fit. And that's when the equivalent circuit that you choose should mirror what's actually happening on your electrode surface, the phenomena that are occurring. Okay. I think we'll call it here.
Yeah.
Okay.
Yeah.
So Sidhu, I do
Sorry,
see there's a
Sidhu.
couple of questions, and there were a couple that I wanted to get to that didn't. But we got to actually a couple of the saved ones, which was better than nothing. But we'll save your question for next time, Sidhu, and we'll try to get to it. But we did answer a few of your other questions. Hopefully we've done our best. I think we got through most everything. So so thank you again for another week. I was trying to just cancel this week and get right to episode 100, but instead we had 2.25 hours of solid questions. So thank you, everybody.
Yes.
I'm going to need to drink a lot of water. My voice is shot and my throat is dry.
Yeah.
But thank you, everybody, very much. It's been nice, and we appreciate everybody as always. And we will see you next time, I guess.
Yep.
So,
For episode 100.
Episode 100.
Show up.
That's right. Episode 100 is going to be a big extravaganza. It's going to be the same, but we're going to pretend it's going to be a big. We should get some big, we should get some balloons or something. I don't want to give away.
Some balloons.
I don't want to give away the excitement, but we're going to have some crazy stuff.
That's
some
a
of
good
the
idea.
crazy celebrations. Until then,
all right.
We'll see y'all next time.
Bye.